Okay, hello. Welcome to the IOA Thursday Colloquium. Today we had the great pleasure to welcome Raffaella Schneider from University of Rome, where she also did her PhD. I believe in there she did a couple of postdocs in Arcetri and then back as a professor in Rome. Raffaella is an expert in sort of early star formation, population 3, direct collapse black holes, and early black holes. And today she will talk to us about all of these phenomena in connection with the latest JWST results. Raffaella, please.
Thank you. So thank you so much for inviting me to give this colloquium here. And well, actually, it's true, as Ian said, I'm mostly working on the high redshift universe and trying to characterize the stellar populations and the black holes that form early on. Today, I will be mostly focused on stellar populations and the early dust buildup in the interstellar medium of these high redshift galaxies. So I will not be talking about black holes. And as you know very well, in the past 1.5 years, we had this amazing set of new observations from JWST. I just, did this collection of pretty pictures, taking most of them from actually from papers that have been led or published thanks to the extragalactic group here in Cambridge. And what I will be focusing most is on a couple of observational evidences that we are collecting on the evolution of the UV luminosity function at very high redshift, and therefore, the first estimates of the star formation rate density evolution beyond redshift 10, and on the early dust buildup in the interstellar medium of these galaxies. So starting from the UV luminosity function evolution, here I'm showing a collection of observations from redshift 4 to redshift 17 based on the early data release of JWST. This is a collection made by Yuki Arikane and collaborators. And so what you can infer from this plot is that you have a relatively slow decline in the UV luminosity function across this broad range of redshift, and then integrating over the UV luminosity and applying a conversion factor between the UV luminosity and the star formation rate, you can infer estimates of the star formation rate density at this very high redshift. And so despite the error bars, what it seems to be is that there is a slow decline in the star formation rate density evolution, and the star formation rate density is in excess of what you would expect based on a constant star formation efficiency model. And more recently, this has been confirmed by looking only at the samples of galaxies that have been spectroscopically confirmed. And again, you find this is the UV luminosity function at redshift 10 and 12, and you find consistent results where you have detection. And of course, here you have only, at that time, you had only lower limits on the number density of sources that have been spectroscopically confirmed. So more recently, of course, there was an issue that was related to the fact that you may be affected by cosmic variance depending on the field that you were observing. So now I think that the consensus is that you still find this axis of UV bright galaxies despite the different fields that have been observed, and also that with more recent data, it is now possible to push these to fainter UV luminosities. And so here you see some two different determinations of the UV luminosity function at redshift of 9-ish and between 12 and 14, going to fainter luminosity than before. And and what seems to come out of this, first determination of the luminosity function at fainter luminosity is that the evolution at the faint end slope is not really significant compared to the evolution at the bright end that was observed. So there seems to be a different evolution at faint and bright luminosities. So here you see essentially the number density of sources at a UV magnitude of -20. The blue line is the extrapolation of what you would expect based on the redshift 3 to 9 observations, and the red points are the current determinations that you see that at UV magnitude of -20 are in excess of what you would expect based on the extrapolation, whereas if you integrate at UV magnitudes brighter than -17, there seems to be, that seems to lie on the extrapolation. So what is this telling us? It's interesting. There may be something related to the burstiness of star formation, or to how star formation and feedback interacts at very early times. And if you compare the result with a different set of different theoretical models, what you find here is that the models are, not all of them, but some of them are able to reproduce the observed number density at fainter UV magnitudes, but they fail to reproduce the brightest, the bright end of the UV luminosity function. So, as I said, of course, these observations have triggered a number of different, theoretical studies trying to, propose different ways to reconcile the theoretical models, the pre-JWST theoretical models with the observations. And I borrowed this slide from Andrea Ferrara and Pratica Dayal, who led a very nice discussion in a recent conference in Sexton just a few weeks ago, where they were listing the different explanations that, or possible explanations for this tension between theoretical models and the observations that range from a lambda CDM cosmology failure to a different possible stellar initial mass function as you go to lower metallicity and higher redshift, the possibility of dust clearing by radiation-driven outflows that, at the bright end of the luminosity function could help boost the UV luminosity, or an increased star formation efficiency that can have, different flavors, either increasing the stochasticity of star formation or having this star formation to occur almost in a feedback-free way in very specific conditions. So, of course, it's hard to disentangle this different possibility at this stage, but I will be focusing mostly on the second one, so on the possibility that you may have a deviation in the stellar initial mass function. And this is based on several studies that dates back to the mid of the 80s with work by Richard Larson and others, that you expect a transition in the IMF when you get to more metal poor environments. And the idea, in a very schematic way, is that thermal processes are, very important to determine the fragmentation scale of gravitationally unstable clouds. And when cooling is very efficient, the gas becomes highly filamentary and starts to fragment. And the abundance of metals in the gas phase and in dust grains is driving this transition in the fragmentation scales. Okay, so this was based on many different models that developed, in the past now 20 years, and that were implementing a very sophisticated chemical network, but a relatively simplified dynamical evolution in these sort of one-zone models of cloud collapse. And what came out of these early studies is the idea that if you look at the fragmentation scales, there is a sharp transition in the fragmentation scales that is occurring very early on in terms of metal content. So when the metallicity is above a critical value that ranges between 10 to the minus 6 to 10 to the minus 4 solar, and in this range, what really matters is the amount of metals that is locked in dust grains, because collisional excitation of dust grains followed by thermal emission is really capable of driving a fragmentation at very high densities. And so, of course, only thinking about the typical fragmentation scales, which are not, of course, the scale of stellar mass. There is a long stretch between the fragmentation scales and the final stellar mass distribution. We would expect a transition in the initial mass function occurring very, very early on in the evolution of the universe, in the chemical evolution of the universe. And this is what, it has been called the critical metallicity for the POP3, POP2 transition. And this was then later confirmed by using more sophisticated hydro simulations that were then incorporating a more physically sound dynamical evolution of these fragmenting clouds, and which all confirmed that, of course, metallicity plays a very important role, and even the presence of dust grains is really a trigger for fragmentation. However, again, this was at the very early beginning of the fragmentation phase of the cloud. It was not really possible to follow the emergence of a stellar initial mass function from this simulation, which has then become possible more recently thanks to increased computational power. And in this paper, Sung-Myeon Chon did a set of simulations where he was starting from a gravitationally unstable Barnard-Herbert sphere, and he was changing essentially the initial metallicity of the gas. Okay, here you see in these different panels a face-on view of the simulation box of the disk, changing the metallicity from 10 to the minus 1 solar down to 10 to the minus 6 solar. This is the scale of the simulation. So these are, density maps of the gas. And of course, the idea was to try to push further what previous simulations had done, so trying to follow not only the fragmentation phase, but also the subsequent evolution of the fragments and the accretion of the fragments as long as possible, and trying to see the emergence of the stellar initial mass function. So what you see here is, in these plots, overplotted on the density distribution, are the stars, which show stars that have a mass larger than 1 solar masses, and the white dots that show stars with a mass less than 1 solar masses. So even by eye, you clearly see that as you increase the metallicity, you have a lot more of these low mass stars that are forming, and so clearly again metallicity is really a trigger for fragmentation. And you also see that the distribution of the gas is completely different, and this is due to the different the fact that when you are at very low metallicity, turbulence decay before star formation. Essentially, you have an almost monolithic collapse at the center, and you have a very massive accretion disk that feeds the stars that are in the center of the cloud. And so you have, a very a very efficient way to form fewer but more massive stars. When you increase the metallicity, you have these filamentary structures that develops, fragmentation occurs all over these filaments, and the accretion is definitely less efficient. So you have, a more an IMF that is more shifted towards lower masses. So in a more quantitative way, here you see the distribution, so the number of stars that you form as a function of their mass, and again for the same metallicities. And you can see that clearly, as expected, the distribution of the stars, we can call that initial mass function, although it's still probably relatively early in the evolution of these systems of protostars, but there is a clear trend going from the lowest metallicity to the highest metallicity, where the distribution becomes progressively closer to a salpeter-like slope, at least at the high mass end. And here you have instead something that is closer to a log flat distribution. So, compared to the previous studies, these new simulations allow us to say that the transition is expected to be probably smoother than what we thought before, and that you can have a deviation from a purely power law distribution at the high mass end, even at metallicities that are of the order of 10 to the minus 2, 10 to the minus 1 solar. Now, in addition to that, what Soon-Myeon Chon did was also to repeat the simulations, but increasing the temperature of the CMB. And the previous simulations that I was showing were assuming a CMB temperature like in the present-day universe, whereas if you go to higher and higher redshift, you expect the CMB to be an effective temperature floor for both the gas and the dust grains. And this is particularly important, especially for the highest metallicity simulations, because in these highest metallicity simulations, the gas is effectively able to cool down to the temperature floor of the CMB, so it is the distribution of masses will be affected by this increasing temperature, and this is not instead occurring at lower metallicity because the gas remains essentially hotter than the CMB at any redshift. And so if you look now at these panels that are showing the higher metallicity simulations repeated at increasingly higher redshifts, so this is redshift 20, 10, 5, and 0, you see that you have an excess of higher mass stars when you do the simulation at higher redshift because of this effective temperature floor of the CMB. So what comes out of these studies is that you can expect to have a deviation in the mass distribution of the stars that is modulated not only by the metallicity but also by the redshift. And even at relatively large high metallicity, so 0.1 solar, which higher with respect to POP3 kind of metallicities, you would expect that the fraction of stars in this log flat component increases with redshift. Okay, so galaxies that we are currently observing with James Webb have metallicities in this range between 0.1 to 0.01 solar at redshift 10. And then, so based on these simulations, you would expect in these galaxies to have a larger fraction of massive stars compared to what we would find for similar values of metallicities in the present-day universe. So to give you an example of what would be the difference in terms of UV emissivity, with a student in Rome, we have run simple spectral synthesis models for an initial mass function that is fitted to the result of these simulations, assuming a metallicity in this range and stellar ages of 10 and 20 million years, you can estimate from the simulated spectra what would be the conversion factor between the star formation rate and the UV luminosity. And this is for redshift 0, so that would be what you would use if you were to assume a standard salpeter-like IMF. And this is what you find when you take into account the excess in massive stars at higher redshift. So you have a decrease in the conversion factor, which means that for a given star formation rate, you expect to have a higher UV luminosity. And so to get back to the observations with Alessandro Trinca, we used a newly developed semi-analytical model that is called CAT. It has also a nice logo. That is able to follow the star formation and the formation of galaxies and their nuclear black holes, starting from very high redshift down to redshift 4, including physically motivated prescription for star formation and chemical enrichment and black hole growth. And using this model, we were able to predict the UV luminosity function evolution from redshift 4 up to redshift between 14 and 16, comparing our prediction with the observations that you see with these different colored data points. So the prediction of the model is shown by black dots, and the shaded region in these plots show the effect of including this modulation in the IMF that depends on metallicity and redshift. Now you clearly see that the effect starts to be relevant as you go to higher and higher redshift, because this axis in the massive star component becomes important at higher and higher redshift. And if you look essentially at the number density of object with a UV magnitude of -20 at redshift between 10 to 11, 12 to 13, 14 to 16, predicted by the model. This is shown by these histograms. In black, you see what we would find using a standard universal IMF. In blue is what we would find considering also the contribution of the nuclear black hole, which, as you can see, it doesn't make a real difference at this redshift because the black holes are still relatively small. And in orange is what we would find considering a non-universal IMF, having this modulation with, with metallicity and redshift. And these horizontal colored regions show you the observational data, the expected number density based on the observations, with the lower limit here is what you have based on spectroscopically confirmed systems. So what we find is that indeed the presence of a non-universal IMF can at least alleviate the tension between theoretical models and current observations at this redshift, although it still be in tension with the photometric candidates at the highest redshift, being still in agreement with the lower limits. So I think that what we can conclude from this is that a deviation in the IMF is expected based on at least on our theoretical models, and it could alleviate the tension with the observations. It probably, we have to wait for more spectroscopically confirmed systems at these highest redshifts to be able to assess whether this is enough or not, or we need to revise significantly our models. So what about instead the most extreme cases, the population tree stars? The expectation, of course, is that these population tree stars form mostly at extremely high redshift. However, theoretical models have consistently provided a different picture, especially in more recent years. And I show you here a collection of different results. So starting from this panel here, where I show the star formation rate density evolution as a function of redshift based on our simulations. These are 8 independent simulations with a volume size of 50 co-moving megaparsecs, so they're relatively large or medium-sized simulation. And Alessandra Venditti, a PhD student in Rome, has derived an estimate of the expected population tree star formation rate density in the analyzing all the simulation boxes, and this is this red line compared to the total one, that is this blue line. And at the same time here, you see a comparison between our findings and other simulations that have been run on smaller scale boxes or on comparably large boxes, including the CAT semi-analytical model that we were discussing before. So if you look at these plots, this appears quite discouraging because it essentially says that the pop tree star formation rate density is unconstrained based on theoretical models. They are all over the place. They can vary by orders of magnitude at a given redshift. And the reason is that all these models differ in terms of, the assumed pop tree IMF, the way you describe the feedback between the stars and the surroundings. Some of them include on-the-fly radiative feedback, other not. And of course, there are all sorts of complications in making these comparisons. However, there is one common feature on most of these models is that it is expected that a fraction of these stars can continue to form down to relatively lower redshift compared to what would be expected based on the idea that these are the first generation of stars that form in the universe. So this is interesting because all of this model predict that there is a tail of pop tree stars that can continue to form down to the epoch of reionization, or at the end of the epoch of reionization. And so what Alessandra did was to try to go and look for, the environments or the properties where these pop tree stars form at lower redshift in our simulation. So these are examples of halos in the cosmic web at redshifts between 6 to 8, where we do find some pop tree star forming regions. And this is zoom in progressively into these halos, and the red stars show the position of these regions where pop tree stars are forming. And so you clearly see that there are some cases in which the pop tree region is found relatively close to the center of mass of the halo, probably in the outskirts of metal-enriched regions, and other cases in which they are at a larger distance with respect to the center of mass in more isolated and pristine regions. And so by looking at, for instance, this halo here, what we find is that in these two star-forming regions, the total stellar mass in pop tree stars is comparable. The metallicity is slightly different. This is truly pristine. This is, very, very small, but yet not zero. And the metallicity of the surroundings is different. And it is very interesting that at least in this redshift range, between 60 to 70% of all the pop tree stars that we find in the simulation are similar to these sp2 cases. They have a distance from the center of mass of the halo that is larger than the mass-weighted stellar radius. So this can mean even a few kiloparsecs away from the center of mass of the host system. So they are displaced with respect to the center of mass of the host. But of course, in terms of relative fraction of the mass in these POP3 stars relative to the total mass, this is very, very small. So as you can see at redshift 10, so this is the mean POP3 mass fraction as a function of the total stellar mass that Alessandra finds at redshift of around 10 in our simulation. And we find that for a galaxy with a stellar mass between 10 to the 8 to 10 to the 9 solar masses, these are the numbers. So it's really a tiny fraction of the total mass of the galaxy, of course. And it is encouraging that very similar results are found by independent groups working with an independent code and an independent simulation. In this case, it's a zoom-in simulation, so they have even higher resolution. And so it is interesting, the fact that JWST has provided some candidate POP3 star clusters at redshift between 6 to almost 11. And here is the nice result by Eros Vanzella and collaborators. This is a highly magnified POP3 star cluster, and the physical properties that they are able to infer for these systems are reported here. So they have, an upper limit on the metallicity of this very tiny POP3 star cluster, very faint object that is 4 times 10 to the minus 3 solar. And this is the well-known system GNZ11, where Roberto's group have found this helium-2 clump, and the luminosity and equivalent width is consistent with POP3 models with a top-heavy IMF, and the kind of redshift displacement from the GNZ11 system is of the order of 2.5 kiloparsec. They are, similar to, in some sense, to what we expect based on our simulation. So I think this is encouraging, and probably it's a motivation to really think of properly designed ways to go after these displaced potentially POP3 star forming regions in the observational campaign with JWST. Now, turning a little bit on the other side of the coin here, we have been discussing about UV bright systems. Now, what Webb is also providing us is with the evidence that indeed there is a rapid phase of dust enrichment probably occurring at early cosmic times. So starting from pre-JW, so there are many observables that I could have shown you. I decided to show you these evidence based on the redshift evolution of the UV spectral slopes. And so this result is a result obtained by Sandro Tacchella before its pre-JWST data. And you can see that the UV slopes, how they vary with redshift when you bin them in different stellar mass bins. So going from the blue to the red, you go from the lowest bins to the largest stellar mass bins. And you essentially see a very mild evolution over this range of redshift, except maybe for the most massive ones, where you see probably a decline when you go beyond redshift 9. But here they have only a very limited number of galaxies before JWST. Now, if you look at the most recent determination of the beta slope evolution, here you see the beta slope as a function of the UV magnitude, and the different colors show the evolution for different redshift from 6 to 7, 9, and 12. And you see that from 6 to 7, the evolution, you don't see a real evolution in terms of UV magnitude dependence. And if you go to 9, you start to see a decrease only at the brightest magnitude, okay? So the others are pretty consistent. So the first thing that we take out of this is that the beta slope do not seem to evolve significantly out to redshift 9 for galaxies with comparable mass and UV luminosity, except for the most massive and the brightest ones. And so this may be an indication of an early rapid phase of dust enrichment in the ISM of these galaxies. And this, of course, resonates with what ALMA has shown in the past few years when it was possible to do large programs trying to observe the dust continuum emission of high redshift galaxy candidates. So here I showed the result of the ALMA Rebel survey that has targeted UV bright galaxies, so it is biased towards UV bright and massive systems at redshift between 6 to 8. And here you see what we call the obscuration fraction. So it's the ratio between the star formation rates derived from the far infrared luminosity to the total star formation rate derived from the UV and far infrared luminosity. And so you see, this is shown both as a function of the total star formation rate and as a function of the stellar mass. And the blue points are the ALMA, the Rebels galaxies. You see that for a given total star formation rate, you can have very different dust obscuration fraction, and that, in general, you have obscuration fraction that ranges between 50 to 90%. So at least at this redshift, the galaxies are known to be significantly dust obscured. And in the Rebel survey, we had also detected two dust obscure serendipitous sources in the field of a couple of main targets, okay? Just by looking around the main targets, it was possible to identify systems that were completely dust obscured. You don't see them in any Restframe UV images, but you can detect the C+ emission, so you know that they are at the same redshift of the main targets, and you see also the dust continuum emission. And so for these serendipitous sources, Yoshi Fudamoto was able to derive some of the physical properties, and it's very interesting because the physical properties of these sources do not seem to differ significantly from the main target one. So they are on what we call the galaxy main sequence. So they have standard star formation rates for their stellar mass, and but they are significantly more obscured compared to the main targets. Okay. So in order to try to understand, what is occurring at this extremely high redshift, we need to think of the fact that when you go to higher and higher redshift and you are probing younger and not younger stellar populations, you are actually getting close to probe really the dust formation, dust injection timescale. So here I show a plot that is taken from a recent review that we have written with Roberto that shows the ratio between the dust mass to the stellar mass. So you're assuming that, a very simple model, you assume that you have a burst of star formation occurring at redshift 20, and then you follow the dust injection timescales considering the main sources of dust. So these is what you expect for supernovae, depending on, the shaded region spans a metallicity range. When you account for the fact that some of the dust that is injected from the supernovae can be destroyed by the reverse shock, and so it decreases the amount of dust that can be injected in the ISM, and this is the cyan-dashed region. And then the green one shows the contribution of Wolf-Rayet stars, the red one from red supergiants, and this yellow range shows the effect of AGB stars that, of course, start to contribute at later times, okay? So what comes out of this is that in the first 30 to 40 million years from the onset of star formation, you expect dust enrichment to be completely dominated by supernovae. And then, of course, AGB stars start to contribute, and the relative importance of the two really is a very complicated function of the star formation history, the initial mass function, and the metallicity-dependent stellar yields. But it is interesting because in these very high redshift galaxies, the typical stellar ages that you infer are on the order of a few tens of mega-year. So you're really probing the early phase of dust enrichment. So in order to understand what is the origin of dust in these high redshift galaxies, we have developed this code Dusty gadget that accounts for most of the process that affect the total mass of dust in the ISM. So injection from supernovae and AGB, grain growth by accretion of gas phase metals in the interstellar medium, dust destruction by supernova shocks, sublimation in the hot phase, astration, ejection in outflows. And we can follow this as the grains are processed in the interstellar medium of the galaxies. So more recently, again, using the most recent set of simulations that we have performed, Claudia Di Cesare, a PhD, now a former PhD student in Rome, now a postdoc at the ISTA in Vienna, has investigated what are the properties of the galaxies that we find in terms of, for instance, the distribution of the simulated galaxy on the galaxy main sequence and on the dust mass versus stellar mass relation. So again, these different panels show you the position of the simulated galaxies that are shown with gray dots at redshift going from 10 to 5, 4, compared to the observations. And you see that the simulated galaxy already seem to align along galaxy scaling relations. And then what we are currently doing is to look closer to the properties of the galaxies in this redshift range that is relevant for the comparison with the ALMA detected sources in Rebels. Again, these are 3 different simulation boxes at 3 different redshift beams, so between 7 to 8.5 and 6.5 to 7 and up to 8. And again, you see that the galaxy align on the galaxy main sequence, and this is again the dust to stellar mass relation. And we can overplot here the detected sources, the Rebels detected sources. Of course, dust mass estimates is very tricky because they have only essentially one single photometric point. So it's very degenerate with the assumed dust temperature. And so, okay, what Ido Algera and others have been able to do is to at least find another try to constrain the parameter space by adding another photometric point, and the estimated dust mass in this case increase with respect to previous estimates. Clearly this is still very, very uncertain despite, this is the best that we can afford, at least now, at these redshifts. However, what you can clearly see is that some of our galaxies have dust masses that are as large as inferred from the observations. Now, you can also look at the dust and gas distribution in some of these systems, and you can clearly see that it's very clumpy, it's very homogeneous, and it extends to kiloparsec scales. For some of these systems, we have post-processed the simulation outputs with radiative transfer with SCIRT in order to predict the spectral energy distribution. And so what I can show you here is the flux density at 158 micron as a function of the UV magnitude. So these are observations from Rebels compared to other observations, again at 3 different redshifts between 6.5 and 7 up to 7.5 and 8. And I can overplot on this the flux density and UV magnitude predicted for our simulated galaxies. In this case, the colored points show you the average value across 100 different lines of sight to the source, and the arrow bars show you the minimum maximum value along individual line of sights. So what we can find here is that if we restrict the comparison to those systems which have properties comparable to the Rebel systems, the Rebel sources, these are, relatively massive galaxies with high dust content, forming stars at rates between 50 to 100 solar masses per year. But we have also a large number of simulated galaxies that have comparable flux density in the far infrared, but they are much fainter in the UV, meaning that they are more heavily obscured. And this is not surprising because Rebels, as I said, pre-selected galaxies to be relatively UV bright. And interestingly, if we focus on the two systems that are closer to the Fudamoto serendipitous sources, we find that these sources can be either heavily obscured, or they can be, not significantly obscured, like in this cyan case, but with individual line of sights that are heavily obscured. So this means that, and if you compare the physical properties of these two systems, you see that they are not dramatically different. So this means that really geometry plays a very major role, and that you have, galaxies with comparable physical properties that can appear, significantly more dust obscured if because of the complex geometry and the distribution of the dust in their interstellar medium. So getting back, this is my very last slide, getting back to the question of what kind of sources of dust are needed to explain the dust masses that we are observing. And here Claudia Di Cesare was showing the ratio between the dust mass to the stellar mass as a function of the stellar mass for our simulated galaxies that are in gray at redshift between 6 to 7 compared to some observations. And this is the Milky Way value for reference. And here you see some colored regions that shows you some reference value that you expect based on individual source types. So for instance, if you assume that you have the maximum possible stellar age at that redshift, that is about 650 million years, so you have the contribution of all the stars with masses larger than 2 solar masses. You can have both supernovae and AGB stars, and depending on the strength of the reverse shock destruction, you are here or here. This is the total amount of dust that you expect from stellar sources if no destruction occurs. And instead, if you assume that you have only very relative young stellar populations that are contributing to dust enrichment, you have only core collapse supernovae contributing to the dust enrichment. This is the maximum amount that you can get depending on the amount of dust that is destroyed by the reverse shock. So if it's not destroyed, you are here, or if it is significantly destroyed, you are here. So overall, what comes out of this is that for some of the sources, you may be able to explain this with a maximum contribution from stellar sources only if no destruction occurs. But for most of the sources, you really need an additional contribution from grains that are able to grow by accreting gas phase metals in the interstellar medium. And this has also been found more recently by comparing our predictions with some of the most recent dust continuum detection at this redshift with more than one photometric point, so that the dust masses are better constrained. Okay, and so grain growth is an important factor in order to produce the dust masses that we are inferring from the observations. So I get my conclusion. So I think that JWST observations are really starting to provide important constraints on the nature of the stellar populations inhabiting these early galaxies, on feedback processes, and on the degree of metal and dust enrichment at very high redshift. Based on our theoretical models, we would not be surprised if at the end we find evidence for a deviation in the stellar initial mass function as you go to lower metallicity and higher redshift. And we find that from ALMA data that at reset redshift between 6 to 8, a significant fraction of galaxies are already quite dust obscured, so dust enrichment occurs very rapidly early on and requires, at least based on our theoretical models, efficient grain growth in the interstellar medium of the galaxy. And I think that in the future, the synergy between JWST and ALMA will be really important in order to better constrain the nature of dust at very high redshift. And I thank you for your attention.